you have the time for that, but I got
I don't know.
Yeah.
I don't know. I just have no idea. I don't know. I couldn't even pick.
What are the classes?
I had an instructor one time that he listed his 3.
Maybe this one.
Okay.
It's the only one I
He
need.
thought were the top.
Yeah.
And that was.
I'll take Chem 101. I'll take the Chem 102 and this.
Archimedes, Newton, and Gauss.
Chem.
Yeah.
I
Yeah.
said Archimedes and Newton. We're gonna skip over a bunch of them after Pythagoras and all those other things. We're gonna
Yeah.
Let's do that.
That was his list. I don't know what his criteria was necessarily. I remember him making a very small list on the board.
I feel like Maxwell was
And Maxwell wasn't really any more of a physicist. I think he was trying to say mathematician. So now in his mind, the definition of mathematician didn't include Maxwell.
yeah.
Just like Einstein's not a mathematician, right?
Yeah, but like, well, I said more. I would say that Maxwell, a lot of his annotations, a lot of his work is in mathematics, but he translated it to physics. You know what I mean? Like a lot of his work led him to a lot of his mathematical work led him to that conclusion. Not necessarily like he was a physicist before. So you
Oh no, Maxwell. No, Maxwell was working on this. It's the same as the Newton issue with the calculus. He was trying. Clark was trying. He was trying to get to these basic understandings. I mean, to understand that electricity and magnetism are really the same thing. I mean, that's a profound physical discovery. And you just use mathematics to justify it.
Yeah. I mean,
Not that that's simple. I'm just.
Yeah,
I'm not trying to. I couldn't have done it, but yeah, he wanted to make that that relationship understood. It's been a driving force in physics ever since to relate every single force to one force, which has not been done yet. I mean, that's what Einstein spent the rest of his life doing, right?
I mean, none of the new mathematicians do that.
Because they suck. There's no good mathematicians these
Well, I
days.
mean, in the 1900s, like Riemann,
Oh no, he.
like he rarely gets like when you talk about big mathematicians, he rarely gets. He even has doesn't he have the Riemann hypothesis that's still out? No one has solved yet. Just
Yeah, that's true. You can make all sorts of hypotheses people can't prove. Right?
yeah, but it's like I heard it's so commonly used, it's just accepted that it's like
I don't know. I don't know how much it's used per se.
isn't it used to like find prime numbers?
What's that?
Isn't this hypothesis used to find prime numbers?
Yeah, it's basically regarding a function that deals with prime numbers. It's pretty subtle material.
What do you guys do in graduate level math?
Same thing.
Yeah.
Just keep going. Just keep
Practice
moving.
it over and over.
Can you show me an example?
Of what?
400 level math
400 level man?
on the board.
400. He's gonna fry his brain. He needs to teach us.
It's a graduate level math.
Stop it.
What? Still got time.
I'll just give you a silly example.
Silly example.
We have 1 minute.
Something you're probably somewhat aware of. So, if this is the complex plane.
Okay.
So this is y, x. So now this is the real axis.
Yep. Real axis.
And this is what you call the imaginary axis.
Yep. And why does this thing have a slash in it?
To let you know it's a set. A lot of the set notation has a slash with a capital letter.
Okay.
It's a complex plane. So any point in here, that's 2 and this is 2 here, then this point here would be called 2 plus 2i. What would we call it? That point is 2 plus 2i.
Alright, x is 2 and then 2i to the y. Yeah.
Yeah.
Okay.
So this is 1i, this is 2i, and here's 1 and 2.
Yeah.
It's kind of like the regular real plane, but it's being a complex plane. So if you have a function, we'll call it f x y, I think equals some u x y plus I v x y. So now you have complex value functions, right? So you put some numbers in here, and then you would compute something over here, and it would give you a real complex number, maybe 2 plus 2i, and the x and y are the correct value. So you have some sort of complex value function instead of a real value function. So that could define some sort of curve in this plane. Say it defines like that.
Yeah. But the
Integrating a circle.
okay. But the u represents
The real part.
okay, and then
This would all evaluate to a real thing, and this would evaluate to an imaginary thing.
yep.
So now you have some sort of simple closed contour. In the complex plane.
Yep.
So now let's say you have another function.
Okay.
And this function is defined everywhere in this circle.
Yeah.
And we're going to say that it's analytic, which means you can differentiate, you can take a derivative of it. Anywhere inside the circle, you take a derivative of it.
Okay.
We'll call that function c. C of xy, right?
Yep.
It lives in here. It's analytic. That is differentiable. There's a little more than that, but it can be differentiated in the contour. It's not the contour, it's a function that lives inside the contour.
Okay.
And now what I want to do is I want to take an integral. I want to take an integral of this thing. And integrate z. We'll use d r around said contour L. Okay? So I'm going to integrate this function around this contour.
Yep.
So that's going to be 0.
Okay.
Turns out it's going to be 0.
So what was the question asking?
This.
Oh.
Let's just say it's in that.
Okay.
Because we know something about the theory of complex value functions and a complex plane, it turns out the answer is 0.
Okay.
But now, if perhaps this thing is analytic inside this contour, but yet there's one location, in this case 2 plus 2i, for instance, where it is not analytic, and it turns out this will not be 0 anymore.
Okay.
It will have a value, but non-zero value. And that non-zero value is going to be what's called the residue of this function at that location.
Okay. So residue is that.
The residue of this thing. Now, I didn't tell you what the residue is.
Okay.
But there's something happening around this location. Right?
Something's happening.
Something's happening there such that when I integrate some function around this contour, the value of that whole thing ends up being related to only this one point. Only one point. And ends up being, we call it the residue of the function at that location.
Okay.
This is called Cauchy's residue theorem. And although it's for the complex plane, it turns out you can use this to evaluate a wide variety of integrals in the real plane, which you cannot evaluate otherwise.